Hello students, welcome to the next lecture on mathematical physics, where today's class is lecture number 4, and our objective is to discuss on the vector spaces. So in this direction, up to the last class we have seen an introduction to the notations in the abstract algebra, followed by how the groups are formed, and then further algebraic structures, how they are evolving based on certain properties that are being satisfied by these sets. Okay, that means the set of elements. So ultimately what happened is, in the last class we have seen that starting from the group, we have seen how the evolution takes place to the case of the ring, and then to the field, and finally we have seen the definition for the vector space. So out of these two things, we have to give the attention to the field definition. We are not going to work out many problems for the field, that's not required, but the definition for the field is the most compact and very simple thing, therefore that definition is required. And the prominent example of field is the set of all real numbers and the set of all complex number, and this is certainly something that you must know, because we will be repeatedly using the field as the set of real numbers and the set of complex numbers. And of course the standard symbols will be used with the double stroke letters. So these things are clear from our last class discussion, and we would like to now start with the vector space, and then I'm interested to take one or two problems and solve, and then we will also see what is the meaning of subspace of a vector space. So today we will see these points, namely the methodology of how to deal with the solution to the problem in vector spaces. They are going to be fairly simple, and then followed by what is meant by a subspace of a vector space. So let's now therefore start like this. And what we had in the last class here, let me here show. In the last class we have seen that capital V will be the vector space. That was the standard symbol. Now this kind of notation is something common in the abstract algebra. Always you put a bracket and then you put the set in the beginning. That means capital V is the set here, and followed by whatever operators that are coming for the set. And for the case of the vector space, you know that there are two binary operators, namely the usual addition and the scalar multiplication. So this explanation we have seen in the last class, and therefore these two things will be written down and then close the bracket. So this is the standard way of writing. If you write like this, the meaning is that capital V is a vector space under the addition and the multiplication over the field capital F. This is how you have to read. So for the case of the group, you remember, for the case of the group, how did you write? Here you put a G here, right? So capital G, then you put a plus. There is no multiplication for the group. So this plus will be an arbitrary star operator. So how do you write this? Capital G, comma star is a group. That's all. That was the definition for the group. So this kind of notation is quite standard one. Some people will use the angle brackets, okay, and some people will use this kind of a parenthesis. So there is no big difference for that. So the point to be noted is that this is the standard notation. So when you are going to open book on abstract algebra, notation is the one that is going to give you trouble, or that is the one which is going to stay away from the subject. So if at all people feel that abstract algebra is a difficult subject and they don't want to read a book on vector space or any book on abstract algebra, if the students are feeling this kind of difficulty, then primary reason being that this kind of notation. So once the notation is clear, then if the meaning of the notation is clear, then it is comfortable to read. So reading is very important. How do you read? This is capital V is a set, that should be clear to you. The capital V being the set is going to be the vector space under the binary operators plus and the scalar multiplication over the field F. This is the general definition, but for our situation, in most of our situation, the capital F, the field will be the set of all real number, because real number is going to satisfy all the axioms of the field. That is why we say that F is R. In addition to that, the set of all complex number will also satisfy all the axioms of the field. And these two things are very easy to verify. it hardly takes 5 minutes for you to check. Okay, this is very important. You will have to at least make one checking. Can you prove that set of all real number is a field? Okay, it's only 5 minutes job, and you can quickly verify. And similarly, the set of all complex number will form a field, because it is only a matter of simple arithmetic. Numbers you'll have to add and subtract, etc. Similarly, complex numbers you'll have to add and subtract, and together is the multiplication. So therefore, the calculation is going to be very simple. Only thing is that you'll have to write down those properties. If 10 of them are there, write down 10 of them. Verify. First one is verify, tick. Second one, verify, tick. Like that you have to do. So hardly it takes only 5 minutes for one problem. That means prove that the set of all real numbers is a field. Similarly, prove that set of all complex number is a field. So that is something that must be familiar to you. Only then you'll be able to proceed further for understanding the problems in vector space. So this is the first point. And the second point is that this is, of course, I have explained that elements of the, here the point is already explained in the last class also. This capital V is what we are going to call the set, and each element of the set is being called by the name vector. So remember that the vector is a generic name that we are going to use. Vector is, of course, a vector in 2D vector. Whatever force, acceleration, whatever that you know about the vector, it is of course that vector, but which means that it is a vector in 2-dimensional physical space and the 3-dimensional Euclidean physical space. But it is not, mathematically speaking, we are not going to limit that kind of vector. Mathematically speaking, 3-dimension you don't have to stop. You can always go to n-dimensional Euclidean space. So in which case we say that they are n-dimensional vectors. So that is fine. So in addition to vectors, as I already told you in the last class, you should also remember that they need not be vectors all the time. Okay, they can be simple numbers, they can be square matrix, complex matrix, it can be rectangular, square matrix, whatever it is. It can be a set of whatever matrix. All of them are possible. Rational functions are possible. And then you can have some polynomials, or you can also have set of functions. Where from you get a function means it can be an arbitrary set of function, or you can choose the functions as the solutions to differential equation. So these kind of objects, whatever object that is coming into picture, they all, every one of them, we will be giving the name vector. There is a point to be noted. It is actually element. Element is okay, it's correct name for that. But this being given the name vector space, what do you understand by the vector space means? It is the space in which vectors are living. That is how you have to understand. Then the question comes, what are vectors? Vectors are any mathematical object, starting from pure number, 2D vector, 3D vector, n-dimensional vector, polynomial, whatever comes into your mind under mathematical object, all of them will qualify to stay as an element here. Therefore, vector space means it is the space in which vectors are living. Living means existing. That is the meaning. Okay, you can't show your finger and then tell where it is existing. We all know that the number 1, 2, 3 exists. Everyone knows that, right? But if you ask the question, show me where is 1. Okay, you can only write the 1 and show it on the blackboard. That is not the thing. That is the written number 1. If I don't write 1 anywhere, I am not at all going to write the number 1 anywhere in the world. If it is the case, you know that the number 1 exists. The question is where it is existing. Show me the space means you can't show it. But however, even though you can't show it, that means you cannot put your finger and show where it is. Even then, it is living. Living means existing. Okay, instead of saying living, we say that the number exists. Where it is existing, if something has to exist, you have to provide space. If I have a pencil, okay, if pencil has to exist, space should be given to a pencil. If I don't give any space, then pencil cannot exist. So similarly, if a number 1, number 2, etc., this kind of numbers are existing means there should be a space. That space is a mathematical space. And in particular, because it is satisfying some special properties, what are called the 10 properties, we give that mathematical space a name called vector space. So this is how the terminology is coined by the mathematicians, and therefore everything is meaningful here. Okay, so remember that the field is more powerful than a vector space, because field satisfies two commutative groups, whereas vector space will satisfy only one commutative group under addition. Field will satisfy the properties of a commutative group under addition as well as under multiplication. So therefore what happens is, any field you take, automatically you can verify that it is going to be a vector space. So these things are interesting properties that goes behind the scene. Okay, so provided you learn something and you understand more and more, you will be enjoying this particular subject. But however, a little amount of work you have to do. Okay, like I already told you, that you'll have to verify, or just to make sure that how can I agree that set of real numbers is a field. Just because I tell, you can't just agree it, right? So at least you should have a working knowledge about how it is really true. How can I accept that set of all real numbers can be a field? So for that, a little amount of mathematical workout is required, and then you'll be able to agree for the axioms and the further calculations that are coming. Okay, so with this introduction, with whatever happened in the last 3 classes, I just want to write down or make sure that the most simple examples of the vector spaces I would like to write down. Of course, the reason being that at least you should know the simplest examples of the vector space without doing any calculation. Okay, for that reason this is required. So let us now let me therefore write down some of them. So the first one I would like to write. The first one is, the set of all real numbers is a vector space over the real number field. And the second one is very similar, namely the set of all complex number is also a vector space over the set of complex number. These are the most fundamental things. And in addition to that, interestingly, the set of all complex numbers is a vector space over the real number field. And here I would like to make a point. Just because I am writing, it is not something which is boring. So remember these things. What I am trying to write here is that these are the simplest examples that can be easily verified. By simplest example, what do you mean is that if you want to verify this particular statement, it all takes only 5 minutes time. That's what I mean to say. Okay, you can always have a lot of exercise problems where the question will be that you'll have to verify whether the given set is a vector space. Okay, so that takes some time depending on what kind of problem is given. But what I am trying to write down here is that the most simple situations that one can imagine, and also that at least you should know that these are the vector spaces. So these are the simplest thing, and they have to be noted down, in the sense that these things should be registered in your mind. And these kind of simple things, for example, may come in the say a net exam or gate, where you have the options will be given, one of them is correct, so you can always mix them in a wrong combination, and then they can ask you, choose the correct answer or choose the wrong answer. Like this, questions can come. So I would like to tell that such kind of questions from the abstract algebra are not difficult questions. So that is a point to be noted. I would like to mention that only if you work out this kind of very basic things, then the things will be comfortable for you to even answer the multiple choice questions. So that's what is the point that I am trying to write. And what is interesting here is that they will write something which is not. So capital R, that means the set of real number is not a vector space over the complex field. So over the complex field, there is a point to be noted. So I am interested to give another example where this is not a vector space, because everything is a vector space, right? So what is not vector space? You can easily see that R is not a vector space over C. You compare with the first one, R is a vector space over R. So what is the difference between the first one and the last example is that the field is changed. Which is the set and which is the field, that should be clear. The first one, what I am writing, is a set. This is the set and this is the field. Okay, which means that the set and the field we are considering identically same thing. Okay, that is why certain things are very simple. Usually what happens is set will be something and the field will be something different. Okay, This is how the problems, a lot of problems will be there. But the simplest situation is where the set also is the same thing, field also is the same thing. In such a situation, many things are interestingly, they themselves become vector space. I explained what is the reason. The reason is these things are field already. Okay, this is a field, this is a field. So because this is a field, it naturally so happens that it's also becoming a vector space. But why this is not becoming a vector space is that this is a smaller set. You see that capital, this R represent real number, whereas the field is different. So your operation has to be from a different field. That is why. Whereas here, field under the set is from the same set, and therefore all the axioms will be satisfied. Of course, you cannot write this as the reason that this is R and that is C, that is why it is not. Like that you should not write. How you have to prove that capital R is not a vector space is you have to write down the axioms 1, 2, 3, etc. up to 10, and then show which one of the axiom is not correct, or which one of the axiom is failing. Once you say that the third axiom is failing, for example, no need to check fourth, fifth, etc. The moment any one of the axiom is going to fail, then automatically you stop there and make a conclusion that it is not a vector space. You don't have to check all the 10 every time. Okay, whichever is the first axiom that is getting failed, and at that particular point you can stop and then make a conclusion. Okay, let us continue this. The next example I would like to write is a notation. So let me write down the notation for polynomial. So you write like this. It is the set of all real numbers you write with a double stroked R. Okay, like this you write. And then open a square bracket and put an X here. So this is the standard notation for polynomials. So let me write down that. R of X is the polynomials with real coefficients. Notations are very important, and that's why I am writing them. Because in the question paper, most of the time only R of X will be there. You have to know what it is. You should know what is the meaning of that. So the word real coefficients, that is the reason why there is a double script R. Similarly, if you write for C of X, it is also polynomials, but the coefficients are now complex. That is the meaning. Complex coefficients, but it is once again same polynomial in X. What is the degree that has to be written down? Degree is not there here. We can always write second degree, nth degree, etc. So now we will make an important point about the polynomial is this one. Polynomials of a particular degree, or a fixed degree. Particular means you fix the degree. That is what I mean to say. So if you are going to consider polynomials of a particular degree n, then it does not form a vector space. This is an interesting point to be noted. In the last class, okay, let me therefore explain here. If you see the last class, I have given I think I have given something like 3 problems to verify what is the conclusion, and one among them is about the polynomials. What I told in the last class is that if you are going to consider the polynomials of degree n or less, okay, n or less, anything you can take. N can be 3, 5, whatever number is okay. The easy thing is to consider n equal to 2, so it looks so small. Okay, second degree polynomial, but I have inserted a word or less. Second degree polynomial or less. If it is the case, the question is that prove that is a vector space. So whenever the word or less is there, then this particular object is a vector space, so not can be deleted. But now this is the opposite problem, where the R less is removed. That means the degree of the polynomial is fixed to be a particular number. You choose whatever number. It's a third degree polynomial, 10th degree polynomial. You fix it. Once you fix, and if it is a set of all polynomial of a particular degree, then what happens is it does not satisfy all the axioms of a vector space, and therefore that particular set is not a vector space. So the yesterday's problem I have asked you to do it, but I do not know how much interest you got to get the solution. So this is the very important point, how you start working with this. So at least I would like to explain in the today's class how this is not a vector space. Okay, so if this is interesting, then you will get motivated to even solve the yesterday's problem. So that is why let me try to explain this. It's quite simple. Okay, only these things I would like to consider. So let me put a line now. So I want to put some line, and then so that we can start discussing the solution methodology. So whatever A, B, C, D, E, so that is the some of the simplest example. So from there also I will put a dividing line. So like this, there are a large number of examples, but at least, okay, there is no point in writing all the 100 examples there. But instead, some of the interesting example and simplest example you start learning. So this is how start learning. Then afterwards, you can always solve additional problems. Okay, so now let me therefore explain how to solve or how to prove that it is not a vector space. So the idea is quite simple. Start with the given set is equal to, given set is already there. It's all the set of polynomials. Okay, so you simply write down that it is the set of all polynomials that looks like a0 plus a1x plus a2x square plus etc. plus an x to the power n, because we say that it's a particular degree. Whether you are going to fix the number or don't fix, it's okay. Okay, but you should also tell what is this a0 etc. They all belonging to the real number set. You can also consider complex number set, but you will get the same answer. Okay, real number set is the easier one, so let us consider that. And once you have that, we have a set and the operators are standard addition. That is what is I mean to say usual addition, and the multiplication is scalar, so you have to write down the scalar multiplication. This is the general thing for the case of vector space, always the usual addition and scalar multiplication. So set is given to you, operator is also given to you, and of course the field is a real number field, but that is something important. Otherwise you can't write belonging to R. Okay, field is actually real number, and here the point to be noted is n is greater than 0 only you will be having a higher degree polynomial, and n is an integer. Okay, so these things are the places where you have to pay the attention. N cannot be a fractional value, so that it won't be a polynomial. Let us consider some number for n, something you can fix any number, it's okay. Let us try to fix n equal to 4. Okay, so that you can write down some expression. Okay, so now what we do is, in order to check the axioms, we will consider any two polynomials from the set, so that when you're talking about commutativity, additivity, or associativity, you need two of them, right? Then only you can work. That is the reason why I'm writing like this. So first polynomial, let it be p of x given by alpha 0, something like some constant, some alpha 0. Okay, or then you can write plus alpha 1 times x, then plus some other constant into x to the power 4, because fourth degree polynomial. Here is the point that I would like to mention. You can ask the question, what happened to the alpha 2 x square? See, generally how it looks like, you see here, a1x is there, a2 x square, like that all the terms are there. Okay, the point to be noted here is that all of them, that means all of them means a0, a1, a2, if all these numbers, these are real numbers, if they are not equal to 0, then all the terms will be present. But remember that a0, a1, etc., they belong to the real number. That means belonging to the real number means, what is the meaning is, from that real number set you have to pick up one value and give it for a0. You pick one number from this particular real number set and give it for a1. That is the meaning. Okay, any number you can pick. That is the meaning of this particular symbol. So in that case, what happens is 0 is also one number inside this real number set, and therefore you have the freedom to put a 0 anywhere. Wherever you want, you can put a 0 anywhere. But remember, if you put everywhere 0, what will happen? The entire thing becomes 0. So you have to be careful. That's what I mean to say that n is greater than 0 means, if n is itself 0, if you put n equal to 0, then all the things are 0. There is no polynomial. You will get a constant, right? 0 or 1, like that you will get. So therefore, in order to keep this polynomial as a polynomial, this n should be some number. It can be 3 or it can be 4. So let us consider 4. So if this is 4, then what is, how do you know that it is a fourth degree polynomial? Means whatever you write here, the highest degree should be 4, then only it is fourth degree. If you write a 3 and stop here, then it is a third degree polynomial. So for that purpose, x to the power 4 has to be written down. Otherwise, it is not at all fourth degree. So So there is a fourth power is there. That is a point, and there should be some constant. There is no need that it has to be written down as alpha 4. That compulsion is not there. It is only saying that it is another constant. Alpha 1 is one constant, alpha 2 is some other constant. That's all. So there is no need to say that this should be alpha 4 and etc. So those things are clear for you. Now the doubt that you may get is why there is x square term and x to the power 3 term. This kind of terms are not there here. That's what I'm trying to say. You have the freedom to put a 0 from here and then put it for some numbers a1, a2, etc. If you want, you can put. If you don't want also, it's okay. So I am just taking a scenario where the x to the power 3 coefficient is 0, x to the power 3 coefficient is also 0. We can always do that. So that is what I mean to say. So this is the point to be noted when we are writing any two. Okay, so we have the freedom to choose any two polynomials, but only thing is that the polynomial degree should be fixed value. That is important. That is what is there in the question paper. Okay, once you are going to fix a particular degree, you have to maintain that particular degree for all the two polynomials that we are going to consider. If you are going to do like that, then you can ask the question whether it is satisfying the axioms of vector space. So the aim should be clear what we are doing. Only then you will be able to agree why we are writing like this. It is not compulsory that you have to write like this. You can choose any other polynomial you like. And even it need not be alpha 0, alpha 1. If you want, you can put some number and then keep. You can say that this is 2 plus some 3.1 into x. Then here you can put some 9.3 into x power 4. You can also write like this and then proceed this calculation, and things will be fine. Okay, so this is the first polynomial. Let us consider another polynomial because we need two of them. So let me write down the second one. So the second one, let us say that this is q of x, which we will say that now it is something like beta naught, okay, plus beta 1 into x minus whether it is minus or plus is okay, but now for this purpose I want to take same value. That means alpha 2 into x to the power 4. Okay, so let us you have to be careful that fixed value I want to fix this. So let n equal to 4, that point I want to make sure. Then there is another point to be noted. You will now ask the question, how did you get the idea that q of x should have a minus alpha 2 into x to the power 4? So that is where the interesting thing is. Otherwise what will happen is we are tempted to take plus and then some number like beta 3 x to the power 4. Now the point is that what is the interesting point? Why did we choose like this is based on our original question. What is the original question? That we want to prove that this is not a vector space. When it will happen is, suppose if you add these two polynomials. Why do you want to add? Why do you want to add means you already know that the commutativity and addition is there. It is one of the axioms. Out of the 10 axioms, you know that first vector plus second vector should be equal to second vector plus first vector. That condition should be satisfied. So we are interested to verify whether first vector plus second vector is happening. Which is a vector means p of x is a vector. Remember what is a vector? Vector means one element in the set. One element in the set is this is one element. This is another element in the set. Like that, you can write down infinitely many elements in the set because this a0, a1, etc. will take all possible values of R. Therefore, remember that this set is not a single polynomial. This point I already explained last class also. So that point to remember, this is not a single polynomial. If you put different values for a1, a2, an, etc., you can generate large number of polynomials, and this is a set of all polynomial. Okay, out of that many polynomials, we are now choosing two of them like this particularly. The main reason for choosing this kind of a combination is that when I add this two things will cancel. Then what happens? That is the idea. With that idea only we are now writing. Okay, let us continue and see what happens. So let me write down what is the meaning here. Because we are considering any two polynomials, we have our choice. So whatever I explained, let me write down our own choice for any two polynomials. It is our own choice, whatever we can choose. And we are going to call them by the names p of x and q of x. So this is the point that I would like to write. Call by the name p of x and q of x. So this implies, so what will happen is, let us add them. P of x plus Q of x. If you add them, what will these two things will get cancelled? I get alpha naught plus beta naught, then plus alpha 1 plus beta 1 into x, and that's it. And let us divide it. That should not disturb. So what is this one? This is a polynomial of what degree? This is a polynomial of degree 1. So what is our conclusion is? The conclusion is that after adding, it has become a polynomial of first degree, P of x plus Q of x. But what is our original set? Original set is a polynomial of degree 4. Fixed value, right? Degree 4. So therefore, this polynomial, what is happening is that this does not belong to the original given set. Because first degree polynomial will not be there in the set. Our set is only fourth degree polynomial. So let us go back and see. So what is your original set? The original set is we are fixing n equal to 4. Therefore, original set will be fourth degree polynomial. But after adding them, we got a first degree polynomial. Therefore, what happens is this first degree polynomial will not be there. So it is not belonging to the original set. So our conclusion is that this kind of addition, okay, this kind of addition has led to the failure of the closure property. So that's what I am writing. So the closure under addition has failed. So the moment some one of the axioms is failed, and that's it. We make a conclusion that the given set is not at all a vector space. So the concept and the idea should be clear. Otherwise, the mathematics is not complicated. Okay, the idea you have to get what is to be worked, and you will have to understand. If you want to prove that it is not a particular degree is there, no. If you want to prove that it is not a vector space, then you should get an idea that one of the axioms has to fail. So based on that thinking, you are going to choose some kind of polynomial and do it. So okay, so that's the answer. So you see that some kind of thinking is going on, and if you work out some problems similar to that, you will be getting an idea of what we have to take, what we have to do. That should be clear. Okay, so let me take white color. I want to write another example. Okay, so what is the second example is that let us consider a given set. We will consider one set here, which is going to be the set of integers, which is written down as double stroked z. That is a given set. And what will be an operator? Operator is as usual, usual addition. This is the standard thing for vector space. The usual addition, okay, of numbers. In this case, it's number because z is there. No, z means what? Numbers. So usual addition of numbers, and together with the second binary operator is the scalar multiplication. So these are the operators under consideration. So we have, so in the question paper, a set is given to you, operator is also given to you, and then field is naturally going to be some set of real numbers. So the question is, let us write the question that you will have to verify whether the given set is a vector space. So I'll write down the question. Check whether the capital S comma plus comma dot is a vector space. So you know the understanding of this kind of meaning. You are asked to verify whether the given set is a vector space under the plus and dot. Okay, that's the meaning. So it's very simple one. Let us take the solution. You know what is this z here, which is the set of all integers. So therefore, let us start from -3, -2, etc. And 0 is also there, then positive numbers are there, then it goes to infinity. So it is an infinitely large set, and that is what is given as S. So what is S should be clear. Given set should be clear. We can say S or we can say V, okay, whatever it is. So that is a given set. Now once it is clear, what is the requirement? First of all, if you want to prove that it is a vector space, you know that the minimum, the first requirement is that the given set has to be a commutative group under addition. That should be clear to you. That is, so that's why I will try to write that. We would like to know whether the capital Z. So let me first write the result and then I will explain. Okay, what is quite easy is that we can easily verify that it is a commutative group. Okay, so what I am trying to explain is that once you have this particular thing, what is the first requirement in order to qualify for a vector space is that the given set should be a commutative group under addition. This is the first step. and therefore you have to check. But this checking is too simple. You can check it in 2-3 minutes. You can verify. So that is why I am not doing it. That's why I have written like this. We can easily verify that the set of integers given by this kind of set will form a commutative group under addition. You know how many properties are there? Only 4 properties are there other than closure. So in a minute of 2 or 3 minutes, you can easily see that this is a commutative group, and therefore the first step is a successful one. So once this is clear, then the next one what you'll have to do is you'll have to check for the multiplication. You know what are the axioms? The one is the scaling. Scaling means multiplying by a number. Okay, that is scaling. The second one is the associativity. So these are the related to multiplication. That is what we have to do now. So let me therefore write down what is to be done under the second step. So this the step 2 that will be related to the multiplication. So let me write down associativity under multiplication, because regarding addition job is over. So when you are coming under the multiplication, you have associativity and you have scaling. These are the two things. So therefore we can check one is that we can check about the associativity, and how the equation will look like. We will write down some constant into another constant multiplied by some vector element should be equal to. So this is a demanding condition. Okay, if condition. So either you say if or you demand. Okay, whatever it is. So this is the if condition to be satisfied. That should be equal to the two constant combined together. Afterwards you multiply the vector element. So if this equality is satisfied, we say that associativity is satisfied. So this is one thing for multiplication. There is another thing for multiplication, and that is the scaling. And there is another name for scaling is you can also consider it as a closure property. Okay, both are similar. So therefore let us write down what is that. So is scaling property I won't write. So the terminology we can use could be the closure under multiplication. How it looks like. So closure under multiplication means how it looks like is, because it is actually a scaling property, we have to consider, or we have to demand. Let me write down, we have to demand a constant times the vector should belong to the same set. That's what it is. And here what is the constant is it should belong to the field, and field is a real number, and we should belong to the vector space, which is S. We should belong to the given vector space S, capital S. So the same thing is true in the left side of associativity. So I will simply write down where K1 is belonging to the set of all real number, that is field, and K2 should also belong to the field, and the vector element V. Okay, and the vector element should belong to the given set capital S. Now this is the place where you have to focus your attention. These things has to be written. If you don't write, then things are chaotic. You don't know what you have to do, and you don't know what number to consider. So therefore let us consider a particular value 2/3. And given vector you'll have to choose some number, and you know why we are choosing 7. You can choose anything. You see what is the set. The given set is this one, right? 1 2 3. Negative is also okay. You choose some number. Okay, simply I am choosing 7 there. And 2/3, why did I choose is it's a set of real numbers, so let us choose some fraction. That's all about it. Then what happens to the K times V is 2/3 times 7, right? So that becomes 14/3. Now the 14/3 is not there in the given set. Given set is what? Given set is integer, right? Now where is 14/3? 14/3 will not be there. So you have now come to a stage where our element is going or escaping outside the given set, and therefore we can quickly write down the conclusion. So that the closure property under multiplication has failed. So now you understand that associativity we did not check, of course. Even though we have written it, we did not check, because we already got the result, right? One result is failed, so there is nothing to do. So we can quickly write down the conclusion that the given set is not a vector space. Not a vector space. VS means, I will say it for vector space, of course under the given field. So you are now able to understand how we are proceeding, or what are the steps that we are writing. So that is something you have to be careful. In the case of the competitive examination, of course you can always choose one of the 4 options. Okay, so the writing ability may not be required. But in the case of the the usual end semester examination, you have to write the details for getting the solution. So what is to be written, that's what I am explaining here. So when you are going to solve one or two problems, you know what is to be written, how it has to be written, okay, and how we are obtaining the required conclusion. So okay, I would like to go to another place in the board and different topic. This, I think, one or two example we have taken. I would like to introduce today the concept of a subspace. Okay, so let me therefore write down subspace. What is meant by a subspace? It is quite simple. The concept is very simple. That the subset is what is going to become here is that the subset has the ability to become a vector space. Okay, has an ability. That means it also has the ability to not become a vector space. So both options are there. But our interest, why we are studying about the subspace, is that we would like to know this, whether it is going to become a vector space or it is going to fail to become a vector space. So the question then comes, how will you check this? So how to check if a given subset is a vector space or not? So that is a natural question that comes. And interestingly, okay, how a subset is a vector space? VS is vector space. And interestingly, this checking mechanism is easy. Okay, so let me therefore write down the practical method. The practical method is that you first of all verify whether 0 element is there or not. Okay, the element 0 should belong to the subset. That is what I mean to say. This is the practical way of doing the checking. I will explain once I finish this writing. It's the first point. Second point is you have to verify whether the set is closed under addition. Okay, verify whether the given subset is closed under addition. That's the second one. The third one is once again closed under multiplication. So if you do only 3, okay, if you do only 3, you will be in a position to immediately make a conclusion. So only 3 points are there, so I'll put a box, and since it is easy to verify, I have written easy there. Okay, so here let me explain something here. Okay, so here points, what is to be noted here is that what do you mean by a subset? First of all, so subset is something which is which must be quite familiar to you. Just for information, I will write down. See, if some set is there here, s equal to some numbers are there. Let us say -10, -9. Let us say -1, 0. Then some 2, 7, 9, 3/2. Suppose that there is a set like that. Okay, set means it is a set of elements, and elements are number. That's all about it. And what do you mean by a subset is, so we can say that subset, let us give the name SS for example. Subset means simply you have to choose some numbers from here and write down. That's all about it. How many number? Minimum 1 should be there. It should not be empty. You cannot close the bracket and keep it empty. If it is empty, then we say that it is empty set. So empty set we will always we don't want to consider, and that is why most of the time you have to be careful to write non-empty every time you would write. So you have to always write down that the given set is non-empty. The point is to make sure that this fellow that is inside the bracket some number is there. That is meaning. So therefore, in order to make sure that this is a non-empty subset here, some number has to be written. Minimum number. Okay, at least one number you have to write. But it is not that always only one should be there. You can always write some numbers from here. For example, -9, 7 and 3/2. If you write like this, yes, this is a subset. So everything is so. The concept of the subset is very clear, that take some part of this and then write it down, then it is a subset. Then naturally question comes, how many subsets are there? Okay, you can always form large number of subset if a particular set is given. So those things are very clear. Now the question is what is the connection between the subset and a vector space? These two things are different, right? Subset means it is a set only. Now the connection, or what we are discussing, is in what way the subset is going to be to become or it will qualify to become a vector space. So that is the concept, and that is why we are now discussing. Okay, if it is successful, okay, let me write down. You have two options. The subset can successfully become a vector space, option 1. Second option is the subset can fail. It can fail to become a vector space. So both options are there. Okay, so you can say that whether it is becoming a vector space, yes. Whether it is becoming a vector space, no. Both options are there. So if it is yes, what happens is this particular subset we are going to rename. We'll give the rename. What is the name that we are going to give is subspace. So this is the name we are going to give. If it is no means you simply forget. There is no more discussion. So now you see this is sub, this is also sub. Now afterwards this portion is set here. This portion is space here. So as you see the space is coming from vector space Vs. So subspace means it is a subset which is qualifying to become a vector space. So the terminology subspace and subset, that distinction should be clear to you. If it is clear, then we can now discuss further things. So now you see this is subspace, this is subset. Okay, so the distinction should be clear to you, when it will become, when it will not become. So that is what it is. So naturally the question comes, how do I know whether the subset will become a vector space or not? Practically speaking, it is an easy method is there where you only verify 3 properties, and all the 3 properties are also easy properties to verify. How it is easy means you have to verify whether 0 is there or not. Whether 0 should be belonging to means what? 0 should be there. If 0 is not there, immediately you reject. And now in this particular random example, simply I have written some number. In this random example, you verify whether 0 is there or not. 0 is not there, right? So immediately you say that this particular subset has failed to become a vector space. Like that you can make a quick conclusion. So therefore that is the reason why I have written easy here. So first test is very easy, and the closed under addition, closed under scalar multiplication, you already know. Just now we have done some 2 examples. Even in the yesterday's class also, the closure property failing we are always checking. Therefore closure property checking is another easy checking mechanism. So we will discuss more about this later, but before discussing some points about the subspace and subset, we will take an example so that you will feel more comfortable in the terminology or in the way in which you are going to deal the solution. So let me therefore, I want to write down an example now. I'll move down, okay, so that I can have space to write. Okay, so the example problem is a simple problem. What is given to you? Given the set S is given by a vector that looks like this. A vector that is looking like the 0, B and C, in which the double colon means where B and C belongs to the real number field. And that's all. That is the given set. So what is given to you is a particular set is given. But I would like to mention, because this is a subset, I want to write down. I will remove this given. I want to say that this is subset. Okay, we are discussing subset, right? So I forgot to write SUB. Okay, so what is given to you is a subset is given to you, which is given by the symbol S, and that looks like that. Then where is the original vector space? So it is also given that original vector space is some symbol V. We will maintain the symbol capital V for that. Okay, what is the given original vector space is capital V, which is nothing but R3. So let me therefore explain R3 and then come, and then later I will explain. In addition, what is given field is a set of all real numbers. That is a given field. Now the question is verify if the given subset is a vector space or not. Vector space or not. That's all. So that's all. That is the question. Okay. So So before we discuss about the solution, I would like to explain what is this R cube. It is not cube actually, you have to read it as R3. So first I will explain what is R3, then we will proceed further. It's very simple. So R3 means a set of all three-dimensional vectors. That's all about it. You know what is three-dimensional vector? Force in three dimension, you know. Okay, how it looks like. Okay, let us take an example with the real numbers as components. So how do you know that real number? And that is where the R comes. Okay, the double stroked R. That is why I am writing real numbers. So you let us write down. Then it will be easy. Something like 1.4 in x direction plus 3.2 in y direction and minus some number 7 times z direction. So this is an example, and that can be written in a vector form like this, like column vector. I mean 1.4, 3.2 and minus 7. So you see that is a column vector. So you don't have to worry about the unit vectors now. So this kind of numbers, okay, or we say that such kind of set of all such vectors. Okay, I have written 1.4, 3.2. You can write whatever number, right? So you will get a large collection. That is a set. So set of all such vectors is what we are going to denote by R3. You read it as R3, not R cube. There is no cube there. It is R3. So R3 means 3 dimension, R2 means 2 dimension. That's all about it. Rn means n dimension. So once that kind of symbol is clear, now let us go back to the original vector space. Original vector space is this is R3. So that is why I am explaining. The given vector space is R3. That is given to you. Here, okay, I would like to explain one more point here. I will write down whatever I am telling, but let me first explain what I mean to say. Now it is given, what is given to you is original vector space is capital V. What is the vector space is set of all vectors in the 3 dimension. This is how you have to read. This one how will you read is set of all vectors in 3 dimension. 3 means 3 dimension. So if you collect all vectors in 3 dimension, and that particular set is becoming a vector space. It's already becoming, you are not checking, okay, it's already given in the question paper that it is becoming a vector space. Now what I am trying to tell you is that you take some time means hardly 5 minutes. Once again, remember, just 5 minutes you can prove. What is that you want to prove is, prove that set of all 3-dimensional vectors will become a vector space. This is the question that I am trying to tell. I did not explicitly write down the question, but you understand what I am trying to say. Okay, prove that set of all 3-dimensional vectors in the real space is a vector space. That means you'll have to prove that this particular set of vectors will satisfy all the 10 properties. Okay, so 10 properties, hardly all of them are very simple because you already know 3D vectors. Okay, the usual Euclidean vector in the ijk direction. You know how to add, you know how to multiply with scalar. Everything is quite simple. So in 5 minutes you can make a proof. But remember, only when you work out like this, then only you will get more and more confidence and then interested to read. Otherwise sometimes it will be boring. Okay, if you feel that it is boring and if you leave it now, you have to leave it forever. That's it. So this is the story about learning. Okay, so certain things has to be very elementary things only I am asking you to do, and only when you work it out with a paper and pencil, you will be comfortable to learn. Okay, so this point is very important. So let me therefore write down whatever I told you now. Okay, so this is fine now. Okay, let us start now. A given subspace. What is the subspace given to you? Is looking like this. So that is subspace is also 3-dimensional. So you see column vector is given 0 BC. But you should know what is B and C. So that is also given in the question paper. B and C will belong to the real numbers. So this is not R3, remember, this is just a real number. So R only is there. R to the power 3 is not there, right? So it is only real number. So R is different, R3 is different. So notations, you have to be very careful. Okay. So once you understand this, we have to verify whether 0 is there or not. So let us make some particular point. Are you able to agree? So are you able to visualize? So let me therefore write down. So just now I told you what is a subset. So are you able to visualize, or will you agree that the given subset is a subset of V? So that is what I am trying to say. So what I am trying to say is this particular symbol. Let me therefore explain what is this S here. The S and V has to be clear to you. Okay. So what is S and what is V? S is a subspace. So this particular symbol is a subset. So that is a symbol for that. Okay, because we have been discussing here as a random example, the subset that we are going to use, right? So for that particular subset, we say that we use this particular symbol. So SS is a subset of the capital S. Both of them are set only. This is also set, that is also set. Only thing is that this is a smaller set. So this particular symbol is, I think, hopefully this is quite familiar to you. So this is one thing that should be now noted down. So that is what I am trying to explain. And once this is clear, we can again come back here. Now you will be in a position to agree whether S is a subset of V. That's what I mean to say. So once these things are clear, then we can now verify whether 0 is there or not. You know what to do now. We have to check whether 0 is there or not. Okay, so these symbols are clear. So now we are ready to verify whether 0 vector is there or not. Okay, as usual, I just now told you that we should not have a non-empty set, so there is nothing to verify. So I am writing the conclusion, first point. Let us now check whether 0 is there or not. That is the one that you will have to check. Whether S has 0, 0, 0. So you have to tell whether yes or not. It is very easy to say. What is B and C you have to verify. Okay. You verify what is B and C. B and C is the element of R. Real number. Real number has a 0, right? Therefore, S has a 0 element. That's all. So the conclusion is quite simple. So these two things are very straightforward. And then only small thing you have to do, or small calculation you have to do, is regarding the closure property. So closure property is one small step you have to do. So let us do that. First of all, let us do the closure under addition, and then we can also do for the multiplication. Sometimes you can combine and do together. So you have to consider some scalar multiplication. You know that scalar multiplication is always there for vector space. So some scalar lambda multiplied by some vector u1 plus some other scalar mu, another vector u2. So like this you are going to consider. So let me therefore explain why we should consider like that. Once you understand what is the set, then you will be able to understand what it is. Okay, first of all, first question that comes into your mind is why did we write like this? That is the thing. So the answer is this. What is our aim? Our aim is that we have to verify closure property under addition as well as under multiplication. So two operators has to come. Now if you are going to consider like this, you see that the scalar multiplication is coming here. Lambda is a scalar, u1 is an element of the vector. u1 is an element of the vector. That is why I have written down here. What is our given subset here? The subset is the set of all elements. Now how the set of all element will look like, maybe I will write it in a rough place. I will go to a rough place or rough paper, and then I will explain here what do you mean by that. This particular subspace S given to you is going to look like 0 BC. That is what is given. And what is BC? B and C is set of all real number. Any number you take, it's all fine. So which means that if you are going to fill the numbers, the first element you don't have any freedom. 0 is given. No way you can change. B and C you have the freedom to put whatever number you like. For example, I can put a 1.1 minus 7. This is one element. You can fill anything. It doesn't mean that you have to fill in a particular order, nothing. Increasing, decreasing order, nothing. So 0 should be the first element. B and C, anything. I can also choose 0, 0. That's what I mean to say. Because it has to belong to the real number. 0 is belonging to the real number. So I can put here. Once again, 0 is belonging to the real number. So it's another. And like this, you can fill so many numbers, and therefore this is actually an infinitely large set. This particular infinitely large set is the subset given to you. So in this particular situation, I can consider one element as u1, another element as u2, another element as u3. So therefore, instead of writing this big bracket and writing like this, the compact notation or comfortable notation is to say that first vector element is u1, second vector element is u2, etc. And you have, if it is nth one is stopping, then you can write the nth one. Because it is infinitely many, we don't want to stop at nth level. So it is actually, we have to close the bracket here, meaning that it is infinitely large set. In fact, u is an optional one. If you want to say that v is a vector, we can always say that v1 is a vector, v2 is a vector. So it's a kind of symbol. Okay, whatever symbol you like, it's okay. So in this case, you now understand when I write s is equal to u1, u2, u3, you can understand what it is. They are actually representing this kind of thing. Okay, I'm not going to say that u2 is 0, 0, 0. It's not like that. u1 will be one set of number, u2 will be another set of number, u3 will be another set of number, and somewhere in this particular list 0, 0, 0 will be there. That's all. So this is the concept, or this is a visualization that you should have in the mind, so that you can understand, yes, has this 0, 0 element. Where it is there, whether it is in the third place or in the 21st place, that is not important. We neither know that where it is, but it is there. That's what it means to say. And similarly, now you see that the set is going to have a large number of elements written down like u1, u2, u3. In such a situation, I can create a scalar multiplication because of this particular term, and at the same time I want to consider the closure under addition, and therefore I have to add another quantity. Okay, this kind of addition is what is known as linear addition or linear combination. So basically, linear combination is some terminology which everyone is familiar, because right from simple harmonic oscillator, you always know that the second order differential equation will have two solutions, and the linear combination of the two solution is a general solution. So this terminology is something that you are quite familiar. So you know this kind of multiplication and this kind of addition is a linear combination. That linear combination, if you do, then you can now simultaneously verify. That means in one calculation, you can verify whether the closure property is satisfying or not. In case if this is failing, that's it. So either it is failing under plus or it is failing under multiplication, and with whatever reason, if it is failing, then that's it. You can say that it is no longer a vector space. So first point is that I am trying to explain how do you know that we have to write like that. Okay, so it is not that we see some book and copy here. That is not the point. Okay, you need not write. In fact, truly speaking, you need not write this. You can do another way. Another way means you can only calculate u1 plus u2. Forget about lambda mu. Lambda and mu can be chosen to be 1. Then what will happen? Only u1 plus u2. So do a separate calculation for u1 plus u2, and then you verify whether that belongs to the original set. That is the closure under addition. And then do the calculation only for lambda times u1. Only one calculation. That will tell you the closure under multiplication. You can also do the steps like that. So 2 steps you can do. But here I would like to show you that in 1 step you will be able to verify both the closure and multiplication in one calculation. So these are the ideas that are going so that you know what you have to think and write what is to be done. That is the point to be noted. Okay, let us now continue here. Okay, that screen is going. Okay, so now it is clear. Okay, and let me therefore write down what is this lambda and mu. Lambda and mu has to come from field, and here the field is the real number space. Okay, double stroked R. This is not R3 once again. Okay, field is R only. So once this is clear, now we will now substitute what is u1 and u2. So lambda times. So how u1 will look like? U1 will look like 0 BC. So 0 B1 C1. So because the first element, right? Simply you write like that. without numbers. So similarly, you can write down 0, B2 and C2. So once that is clear, now you know how to add, because these are the usual vectors in the 3 dimension. So you know how to add it. Okay. So therefore that gives you, the first element is actually lambda times u1 plus lambda times u2. That means the first element will be 0. Second element will be lambda times b1 plus mu times b2, and similarly the last element. So now the point to be noted is that, let me write down what is to be noted here. Each one of them, whether it is belonging to the real number or not. Okay, you will be in a position to agree that everyone is a single number. It has to be, because lambda is a number, b1 is a number, mu is a number, b2 is a number. So everything is a number, and therefore we can write down that instead of writing lengthy expression like lambda times b1, etc., we say that alpha is a number, beta is a number. So ultimately what happens is that 0, alpha, beta, how it looks like is, it looks as the original, it looks as if it is looking in a very similar way like 0, BC. It looks like identically same. Instead of BC, now you have alpha, beta. And therefore, you agree that this has to belong to the original subset. So that is our conclusion. So therefore, what happens is lambda times u1 plus mu times u2 is belonging to, or that particular object is inside the subset. So this means, what is the meaning of that is, closure property is now successful. But since we are using plus and multiplication, it is simultaneously satisfied in one stroke. Okay, that is what I mean. We did not do two calculations. In one calculation itself, we have done this. This is the point to be noted. And therefore, we can write down the conclusion. I'll write down that. So the conclusion is, therefore, okay, hence the subset is a vector space. Okay, subset is becoming a vector space means I already told you that is called a subspace. So that particular terminology should be there. Subset is becoming vector space. Such a vector space is known as subspace. Or that's all. So this is the solution, and so you get an idea regarding how the problems in vector space will look like, and how you have to proceed, and how you have to think. So these are the things that you are able to see now. I would like to explain a little bit on subspace, but this board is full. I'll go to another place. I would like to explain a little bit on the subspace and the subset with an example, because I already explained, but let me again explain once again formally. These are explained to you, so you can easily follow. Okay. So given some kind of a set like that, and the subset can be any number you write. Choose any number. I am choosing randomly two of them. So this is a subset, so you agree for that. And the question that we have to address is, the question is this: if the original set, this is the topic. If the original set is a vector space under the field, then is the subset also a vector space? That is the question. Is the subset also a vector space under the same field? Under the same field is important. Okay, field cannot change, operator cannot change, so that is important. So in our discussion, namely subset, subspace, what is the main topic is, this is the main topic. We have to verify whether the subset is becoming a vector space. So for that, the notations are standard notation. I will write down. The standard notation is this one: original set which is already a vector space. Okay, which is a given vector space. I will write V as is V. It will be a comfortable notation. And then the corresponding subset, you write it down with a symbol capital S. The point to be noted is that these things has to be worked out under the same field and under same operator. They should not be changed. Okay, there are V is there, S is there, right? In both V and S, field should be same, operator should be same. Okay, so already explained this one. If it is yes or no, what will happen? So that point I will write down. So you are going to make a easy checking mechanism with the three steps. And once the subset is becoming a VS, once if the subset is also becoming a VS, okay, if it is yes, then we are going to rename. That's what I'm trying to say. We are going to rename subset as subspace. That's all. So this is the main concept here. This is the first point. The second point that I would like to explain here is, let me so this is okay. This is I would like to put a line now. Let us now next write down. I want to take a simple example, the most simple example, by the way, and to introduce a terminology. I want to introduce a terminology. So I'll take a special or simple example. This example is going to be a very simple one. And the main purpose is that I want to introduce a terminology called a singleton. So for that, let us take a vector space as a two-dimensional set of vectors, and let us consider the subspace given by 0, 0. So subspace is now having only one element, and the field is going to be the set of all real numbers. And now the question is now clear for you. What is the question is, you'll have to verify whether the given subset is a vector space or not. Okay, subspace is becoming subset is becoming vector space means the question terminology should be clear. Subspace of V. So that terminology should be clear. That's why I have explained for some time. This is the simplest problem. We can easily do this in 1 or 2 minutes. Let us see how it is to be done. First point you observe is that the subset is not empty. So this is always easy to write because there is one element, right? 0, 0 is there, so it is not empty. So first point is clear. So what about the operators? Operator is as usual. That means the usual addition together with the scalar multiplication. So in most of the vector space problem, this is the situation. Okay, the normal addition and scalar multiplication. That should be clear to you. So once this is clear, the first point is clear. Second point is that 0 vector is there or not. So you already know, right? What are the 3 points? Second point is 0 vector is there or not. The answer is yes. It's a given s itself is 0. The third point is whether the closure property under addition is there or not. Whether the closure property is there or not. So let me then write down. But point to be noted is I already told you that there are 3 points are there to be checked. Okay. This is clear. Non-empty means because there is some element, right? So this is not empty. Clear. There is another point I did not write. What is that point is whether the subset contains 0 element. So that is 0 itself is given here. So there is nothing to verify, right? 0 element is already there. So therefore, if you want to write down that the subset is contains or it has a 0 element, okay, and then put a tick here. So I just want to say that I have skipped it because already 0 is visible there. And once that is clear, next point is verifying the closure under addition and closure under scalar multiplication. And the calculation is going to be very simple because only one element is there. So let us do that quickly. So if the first element is 0, 0, then what is second element is? Second element is also 0, 0. That's what I mean to say. There is only one element means all elements will be always 0, 0 only. If it is the case, your addition will give you this kind of addition. And this is the normal addition that you do in the two-dimensional algebra. So therefore 0, 0 is the answer. It is belonging to the set. Okay, so therefore it is successfully we have checked the addition, closure under addition. Similarly, this kind of small exercise you have to do for scalar multiplication. Therefore, closure under scalar multiplication. Once again, this is going to be the very simple one. So how the scalar multiplication closure addition looks like is that you need a scalar, you need a vector to multiply. So let the scalar be k and let the vector be u1 as usual. So u1, what is u1 means 0, 0. It is given to you. You can't change it. So if it is the case, you take a product k times u1. So k times u1 is what I say scalar multiplication. So k times 0 0 is 0 0. That's all. And therefore 0 0 is belonging to the subset. Therefore once again this is successful. So what happened is all the three properties or the whatever properties are satisfied. Therefore our conclusion is that the given subspace containing only one element is a vector space. Okay, so that's all. That's what I am now writing. These three tests that we have written, our conclusion is this. Even though we have done three tests, what happens behind the scene is this one. Something is happening behind the scene which you do not know. That point I am writing. What happens is it automatically guarantees that all the 10 axioms of the vector space are satisfied. All the 10 axioms of the vector space are satisfied. So this is something important because you are not going to verify all the 10 of them. Even though you are not verifying, it happens naturally. Okay, so there is a proof for that, but we are not going into the proofs right now. So you have to see how many 3 tests only you are doing, but even though you are doing 10 of them, 10 of the axioms are automatically satisfied. Axioms, okay, S is missing. So 10 axioms are automatically satisfied even though you are not verifying. So there is a theorem and there is a proof for that, that this is really taking place, and therefore you have to be happy about that. That is why I told that this kind of methodology is easy method to check. Okay, finally let us make one important conclusion. We have only one element in a given set, right? 0 0. So there is a special name for that. Whenever a set is having only a single element, that particular set is known as singleton set. So you can see single there, right? Single means what? Only one, right? So I am just making the connection. If there is only one element, that is known as a singleton set. So in order to introduce this particular terminology, I have chosen this problem. Sometimes in the question paper, no, consider a singleton set, like that will come. You should not say that I don't know what is a singleton set. Okay, so the concepts are very simple, but whenever a small problem is done, it will be comfortable. I would like to give a small problem to you, very small problem. Okay, problem means not that you have to run away from here. Okay, so I am going to give you easy problem here. So what is given to you? So let me therefore write down. Given, what is given to you is vector space is given to you, V, which is nothing but a two-dimensional real numbers. I mean two-dimensional vectors, that's the meaning. And also the subspace is, subset is given to you that looks like x, y, where x has to be greater than 0. Okay, let me write down. Where x has to be greater than 0, and the field is the set of all real numbers. And the field, that should be clear. The field should be a set of all real numbers. So only if you know that, you know how to fill the x and y. Otherwise, what value of x and y should be there? That's what I mean to say. So x and y, they will belong to the set of all real number. So that's a question paper, but there is some implied meaning. Okay, in question paper that is not there. So, but I'll write it for you. What is the meaning is that there is no restriction on the value of y. So this is the information you are gaining by reading this. So if at all there is a restriction, it is only for x, which means that x is greater than or equal to 0. So restriction is there for x. There is no restriction on y. This information I am writing it is not there in the question paper. Okay. So once it is, if this is clear to you, as usual, the question is the same. Verify. Okay. Or we say check whether the subset is a subspace of V. Verify whether subset is a subspace of V. Answer I will tell you no. Okay, so now that I have given the answer, you know at least whether you are doing correctly or not. So it is very simple. Hardly it takes 5 minutes time for this. So that is why I told that this is a this is an easy problem. So you should not feel anything. So by doing this kind of small problems, you will gain some interest in learning this particular topic, namely the vector space. And once you are learning in vector space, much of abstract algebra is not there. So things are standard things. In particular, this kind of R2. What is R2 means? It is like 2i plus 3j. 2i plus 3j is a standard two-dimensional vector. Now that kind of vector is what is written down as a column vector. So this vector, if you remove the unit vectors, then you write down xi plus yj. That is this one, xi plus yj, where I is a unit vector in x direction, j is the unit vector in the y direction. So that is what is written as a column vector. So a set of all numbers which is written down with a restriction that x will take a 0 and the positive numbers alone. Negative values are not allowed. That's the meaning. Negative values are not allowed. For y, you fill any number from the real number set. And if such is the situation, okay, if such is the situation, you'll have to verify only three. You'll have to verify only the three conditions, and if all of them are successful, then you say that it is going to become a subspace of V. Okay, the answer is no. You try to prove that which one of the three conditions is failing. That's what you'll have to find. Okay, so try to do this, and let us meet in the next class.